Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures in computer networks. Today we will be looking at the transport layer. We will be looking at the TCP protocol, the transport control protocol, which is used in the TCP/IP suite of protocols. The topics that we will look at today would be the services provided by TCP, header details of the TCP, and the state diagram of the TCP protocol. So just to give an orientation of where we are with respect to the network layer stack. So we are talking about the transport layer, which resides between the network layer and the application layer. And remember, the transport layer is the first end-to-end protocol. So the primary function of a transport layer is process to process delivery. This is something that we have already seen in the previous class, but this is just to re-emphasize the fact. So primary function of a transport layer is process to process delivery. This is also referred to as multiplexing or the demultiplexing functionality. So we say that it provides logical communication between application processes running on different hosts. So this is the primary function of the transport layer. So when we look at transport layer protocols, there are two flavors of protocols that are available in the internet. One is TCP and the other is UDP. We have already looked at the UDP protocol, which is an unreliable protocol, and TCP is a reliable protocol. So what does TCP do? It endeavors to enhance the services provided by the unreliable IP protocol. Remember that IP protocol does not provide any reliable service, it is just a best effort delivery service. So what TCP tries to do is it tries to provide some kind of reliable service even though it runs on top of the unreliable IP protocol, so that applications which require reliable services could make use of the TCP transport layer protocol. So let us look at what are the techniques that are used by TCP for reliable transmission. Now one of the first techniques that TCP uses for providing this reliable transmission is that it takes a connection oriented approach. So what do we mean by connection oriented approach? We ensure the presence of a receiver before we start the transmission. That is, you first establish a connection and then you start the transmission of data. Second is that we use sequencing and acknowledgements. Now we know that with the IP layer protocol you could lose packets or packets could be delivered out of order. So to take care of out of order and duplicate packets, we use sequencing and acknowledgements. That is, we number the packets so that we know which are the packets which are being sent, and we also have acknowledgements which are sent back from the receiver to the sender, so that you can know that data has been transferred reliably, that it has actually reached the other destination. So next, the third technique that is used is retransmission. This is to take care of lost or erroneous packets. That is, when you do not either way, when there is an error in the transmission or a packet is lost for whatever reason, then TCP will retransmit the packet. Now how will it retransmit the packet? Because when it does not get an acknowledgement from the receiver, it identifies that something has gone wrong in the network and retransmits the packet. So retransmission is a mechanism to make sure that packets are delivered to the other end, even if they are lost. The fourth technique that it uses is flow control. Now this flow control handles the slow receiver fast sender problem. That is, if the receiver is very slow, because of that it is possible that data that is sent to the receiver is not actually captured by the receiver. That is, if you have a very fast sender sending data to a slow receiver, then we have the problem of the receiver being overwhelmed by the data that is sent by the sender. So to handle this, we use a flow control mechanism. Now remember that we already looked at flow control when we talked about the data link layer. Now there we talk about flow control just across a single link. Here we talk about flow control from a process to a process. So there is an end-to-end flow control that is implemented by TCP. Next thing that we have is congestion control. Now congestion control again is done to take care of the bottleneck at the network. Now remember that congestion is a phenomenon that happens at the network when you have multiple transmitters transmitting data simultaneously, much more than the capacity of the network. Now in this case, ideally it would be good if the network layer handled the situation, but since the IP protocol does not handle congestion, TCP tries to handle this congestion. So, TCP also includes a congestion control mechanism in order to provide reliable transmission. So, these are the 5 different techniques that are used by TCP in order to provide reliable transmission. So, we will take a look at what is done in each of these, but before that we will take a look at first the TCP segment format. We will see that the segment format, that is the header format, actually includes all the features that are required in order to implement these techniques. So, let us take a look at that. So, if you look at the TCP segment format, you can see what we have here. The segment format is actually organized as 32-bit words or 4-byte words, and you can see that the header, the initial portion, this consists of the header which is followed by the data. The header first starts with a source port number and a destination port number. Now, the source port and the destination port are the fields which are used to identify the process on the source side and the process on the destination side. Okay. So, this is followed by a sequence number field. Now, we just talked about sequence number as sequencing as one of the mechanisms used. So, we use a sequence number field which is a 32-bit field. Now, the sequence number identifies the sequence number of the packet or the segment that is being sent. Acknowledgements number similarly specifies the data that is being acknowledged by the receiver. So, this will be sent by the receiver to the sender. Then we have something called a header length field which specifies where the header ends and where the data begins. So, if you look at this header length field, if you look at this picture here, you can see that the header consists of 20 bytes of standard header, that is, you can see it 1, 2, 3, 4, 5, these up to these 5 32-bit words is a standard header, and this is followed by an options field. So, since we have options, you do not know whether there is an option field present or whether it is not present. So, to indicate that, we have a header length field. Now, this header length field will tell you where the header ends and where the data begins. So, that is the purpose of this header length field that we have here. Then we have there are a few reserved bits, and then there are a set of flags, 6 flags which are used for controlling the data transfer. We will take a look at these flags shortly. Then there is something called an advertised window field. Now, this is a field which is used for flow control. Then we have a header checksum field which is used for error control. Now, you need to identify if errors have occurred. So, we have a checksum. The checksum is the same as what is used in the IP and the UDP checksum mechanisms. And then we have something called an urgent pointer which is used to send data urgently. That is, if you have some urgent data which is present in your in the data field here, then the urgent pointer points to where that urgent data is present or the urgent data ends. That is, if I have urgent data, it would be there from the beginning of the data field up to a particular point. That point is indicated by the urgent pointer. Now, we will come to what is meant by these shortly. So, you can see that whatever is required for multiplexing, demultiplexing, and then sequencing, and then acknowledgements, and then for the various controls that we talked about just now, all these are actually accommodated in the TCP header. Okay. So, now let us look at each of these in a little bit more of a detail. So, let us look at port numbers first. As I said, port numbers, we have a source port number and destination port number, and these are used for multiplexing and demultiplexing to identify the processes at the two ends. This is the same as what we have in UDP, same idea that is used in UDP as well. Sequence numbers. Now, look at how TCP handles sequence numbers. TCP numbers the bytes of data being transferred in each connection. That is, we say that TCP is a byte stream service. So, the numbering is done on a byte basis, and the numbering starts with a randomly generated number. That is, for a given TCP session, the numbering does not start with the value of 0, but it starts with some randomly generated number which is kind of indicated to both the sender and the receiver. So, let us look at how this is done. Okay. So, typically what we have is, you have a sending process which is giving data to TCP, and TCP treats that as a stream of bytes and sends it to the receiving end. And the receiving process, the TCP then sends it as a set of bytes to the receiving process. Okay. So, if you look at the sequence number field which is there in the header, the value of the sequence number field in the segment defines the number of the first data byte that is contained in that segment. That is to say, if I have data bytes 100 to 110 being sent in a segment, then the sequence number field which is specified in that particular segment will have a value of 110. So, let's just take a quick example to understand how the sequencing is done. So, imagine a TCP connection is transferring a file of 3000 bytes. The first byte is numbered at 10040. So, I told you that the TCP TCP uses random numbers to start your sequencing. So let's assume that the first byte of this particular sequence starts at 10,040. Now the question is, what are the sequence numbers for each segment if data is sent in 3 segments, with the first 2 segments carrying 500 bytes and the last segment carrying 2000 bytes. There are altogether 3000 bytes sent, but the first 2 segments carry 500 bytes and the last segment carries 2000 bytes. So the question here is, what will be the sequence numbers for each segment if data is sent in these kind of 3 different segments? So let's look at what the answer for this will be. Now the first segment we know will start with the sequence number of 10,040. So the sequence number field there will say 10,040, and the actual bytes that are sent here will be 500 bytes. So from 10,040 to 10,539 will be the data that is actually sent in this segment. So the second segment will start with the value of 10,540. So the sequence number field in the second segment will have a value of 10,540, and this will have data from 10,540 to 11,039. That is indicating that another 500 bytes are sent. Now segment 3 similarly will have a value starting at 11,040, and this will be a packet which contains 2000 bytes. So it will have a range of bytes starting from 11,040 all the way up to 13,039. So this will cover the entire 3000 bytes that we talked about. Okay, so this is just to give you an idea of how the sequencing is done. Okay. Now coming to acknowledgement numbers, the value of the acknowledgement field in a segment defines the next byte that the receiver expects to receive, and the acknowledgement number is always cumulative. So we always say that we use cumulative acknowledgements in TCP. That is, if I have received up to 200 bytes, then I always give an acknowledgement number of 201, saying that the next byte I expect is 201. Now this 200 bytes could have come as a single segment or as 2 different segments, but when an acknowledgement is given, we always acknowledge the last byte that is received, and the acknowledgement number will be the next byte that is expected. Okay, so that's how the acknowledgement is handled. Now coming to the flags that we talked about, it's important to understand these flags because this is what helps us to control the different techniques that we talked about earlier. Okay, so let's look at the flags. Now there are 6 flags in all. So we have something called an urgent flag, an ACK flag, a push flag, a reset flag, a SYN flag, and a FIN flag. Okay. Now reset, SYN, FIN and ACK are used for establishing connections and for terminating connections. Reset is used when you want to reset the connection in case something has gone wrong. Urgent and push are 2 special flags which are used for handling data in a special manner. Okay. So now let's take a look at these flags. So as I said, reset is the simplest to understand. This is set in a packet when you want the connection to be reset and you want to start all over again from the beginning. Okay. So this is a reset that is used. If something goes wrong, we make use of this reset flag. The other 2 flags are more important, or rather all of them are equally important, but the SYN flag and FIN flag are important for our understanding of the connection establishment process. So let's look at this SYN flag. Now SYN is used to synchronize the sequence numbers during the connection establishment phase. So when you want to establish a connection, you basically send out a packet which has the SYN flag set. Similarly, FIN is used to terminate the connection. So if I want to close the connection, then I send a packet which has a FIN flag set. Okay. So reset, SYN and FIN are used for these 3 purposes. Coming to the other 3 flags, urgent and ACK, the urgent flag is set if there is some urgent data that is being carried in a packet which needs to be delivered quickly to the other side. That is, you're telling the receiver side that this is data that needs to be delivered quickly, or there is some special data that's being delivered, so this has to be handled specially. So that information is conveyed by means of this urgent flag. So if I have urgent data being sent in my packet, then the urgent flag will be set. So it's an indication that there is urgent data present in this particular packet. The ACK field here, now this indicates that the acknowledgement field in your header is valid. Now typically an ACK field will be sent for all the data that is being sent. So whenever data is sent and an acknowledgement is to be sent for the data received, then the ACK field will be set. Now push is another special type of flag which indicates that the TCP should not wait for, the TCP sender side should not wait for lots of data to be accumulated, but should just go ahead and push the data that has just been given in its buffer. Okay, so these are the flags that we have in the TCP field, in the TCP header. Now let's look at how these flags are actually used for connection establishment and termination. So connection establishment that is done in TCP is by means of what we call as a three-way handshake. Okay, there is an important term that's used in TCP. It's a three-way handshake. So let's look at what happens in a three-way handshake. So first, when a client wants to talk to a server, so what it does is it sends out a SYN packet, that is a packet which has the SYN flag set. When the SYN flag is set, it indicates that it is trying to start a connection. So SYN flag essentially means that client tells server, I want to talk to you. Okay, that's the information that is sent by the SYN flag. When it sends the SYN flag, it also sends a sequence number saying that this is the sequence number at which I want to start my data transfer. I told you that sequence number will happen at a random, you start at a random value. So in this case, that random number at which you want to start your sequencing process is indicated in this SYN packet. So in this example, the sequence value that's being specified here is 1200. So I have a value of 1200 as the sequence value, and this is a SYN packet that is sent. On receiving the SYN packet, the server will respond saying that it will, by giving an ACK saying that it has received the SYN packet and it is willing to accept the connection. Plus, since we have data communication taking place in both directions, it's a duplex, fully duplex transmission that is taking place. So the server also sends back information to the client saying that I also want to establish a connection to you and I want to talk to you. So it also sends another SYN. That is, on receiving a SYN, the server sends back a SYN plus an ACK. A SYN as well as an ACK are being sent, and it also specifies the sequence number at which the server wants to start its sequencing process. So in this example, it gives a value of 4800 and it acknowledges the sequence number that was sent by the sender. So the ACK field will be set, the ACK bit will be set, and the acknowledgement number will have a value of 1201, saying that it is now willing to receive data starting from 1201. Okay. On receiving this, now the client side has received now a SYN from the other side. So it also has to send back an ACK for that. So now the third packet it sends is an ACK packet, that is the ACK bit is set, and it gives the sequence number as 1201, indicating that this is the sequence number that it is using, and ACK for the 4800. So it will send back an ACK information of 4801. So this will be the three-way handshake that is used. So you send a SYN packet, receive a SYN plus ACK and send back an ACK packet. Now we come to the 4-step connection termination process. Actually the connection termination process could also be a 3-step process. We will just take a look at how that could also be achieved. But there are 4 distinct steps that are typically involved in a connection termination process. So let's take a look at that. So to terminate a process, when a client has finished transmitting data, so what it would do is that it will send a FIN packet. That is, it sends a packet in which the FIN flag has been set. So let's say 2500 is the sequence number, and it sends this particular packet. Now on receiving the FIN packet, the server identifies that okay, the client has now stopped its data transfer and it has sent a FIN packet. So it sends back an ACK saying that it has received the FIN packet. So an ACK is an indication to the client that this FIN packet has been received correctly. Now once this ACK has been received, a client is no longer going to be sending any data, okay, but the server could still be sending some data. So it keeps its connection open and waits for a FIN to come from the server side. So server, when it has done with transfer of data, it is indicating to the client that it wants to stop transmitting data. It sends a FIN packet, that is a packet which has the FIN flag set. That FIN flag again will be acknowledged by the client by sending an ACK flag. So a packet with an ACK flag being set. So that indicates the completion of the data transfer, completion, and it indicates the termination of the entire connection on both the sides. So you have a FIN, an ACK in response to that. So FIN plus ACK is one set of packets that are sent to close the connection on one side. Similarly, FIN plus ACK on the other side, from the other side, which closes the connection from the other side. Now what could also happen here is that you could have the FIN plus this ACK, which is sent by the server, sent simultaneously. Now when would that happen? That would happen if by the time the client says I have finished my transmission and it sends a FIN packet, server also decides that it has finished its transmission, so it wants to send a FIN as well as ACK the FIN that has been received from the other side. So the server can send a FIN and an ACK together. So in which case you could have a FIN sent, a FIN plus ACK received from the server, and an ACK being sent back from the client. So this would be the connection termination process. Now remember that TCP is a stateful protocol. So once you establish a connection, there is some state information maintained about the data transfer. So we need to necessarily terminate the connection. So we have this 4-step connection termination process. Okay, and the connection termination process, also please remember that the two sides can independently close their connection. So one side sends a FIN, receives an ACK for that. Similarly, the other side sends a FIN and receives an ACK for that. And only after all these 4 steps have been done is the connection terminated. Okay, so now we will take a look at the entire state transition that takes place for this connection setup and for connection termination. Okay, so let's look at what TCP does for this. Now TCP actually has several open options. Okay, so when TCP opens a connection, okay, it can either do a passive open or it could do an active open. So now let's look at what we mean by this passive open. What it does is the TCP opens a connection and waits on a specified port for a connection to come from a remote host. Okay, this is referred to as a passive open. Now in passive open again we have unspecified passive open and fully specified passive open. Now in unspecified passive open, TCP is listening for a connection from any remote host. Now any is the key word here, for any remote host to contact it from any remote host and any remote port to contact this particular TCP server. On a fully specified passive open, it is listening for a connection to come from a specified remote host and port. Now this could be specified by the application saying that it wants to talk only to a particular client. So in that case you would use a fully specified passive open. Otherwise, if you are open for any client to contact the server, then we may go in for an unspecified passive open. The other option we have is an active open. In an active open, you establish a connection to a given remote host and port using the specified local port. This active open could also be with data, that is at the same time as you are doing the active open, you are also including a data segment that needs to be sent. Now you can look at how this will typically happen. Now so let's look at when an active open will be used and when a passive open will be used. Now typically a server would start with a passive open. So a server opens up a port and says, okay, now I have opened up my port, I am willing to accept connections from different clients. The client will start with an active open saying, I want to connect to this particular server and start my data transfer or receive data from the server. Okay, so this is typically the sequence of events that would happen. Now let's go through the TCP state transition diagram and look at how different states are used by TCP to establish this entire process. Now this picture here is a complete diagram of the TCP state transition protocol, which is used for connection establishment and connection termination. Now we look at details of this as 2 different state diagrams. Okay, so let's look at the connection establishment process first. Okay, so now we have 5 different states here: closed, listen, SYN received and SYN sent, and then established. Okay, now let's look at, we'll start first with the closed. Initially the TCP's state is closed, and on doing a passive open, right, it will come to what is called as a listen state. So as I said, the server would do a passive open and come to the listen state. Okay, so it's waiting now for connections to come from the other side. Now a client would do an active open. Now what will be the job of an active open? You will have to indicate that you want to actively start a connection. So you send an active open by sending out a SYN flag, the first part of our 3-way handshake. So and I move into a state called the SYN sent state. In the SYN sent state, what is it I have done? I have sent a SYN pack, I am waiting for a SYN plus ACK to come. So ideally I should get a SYN plus ACK. Now when will I get a SYN plus ACK? If it is sent by the server. The server, which is listening, on receiving a SYN packet from the client, will send out a SYN plus ACK and go into a state called the SYN received state. Okay. Now when the server has sent a SYN plus ACK, the client, which is now waiting in the SYN sent state, on receiving a SYN plus ACK, sends out an ACK and moves into the established state. Now when this ACK is sent, the server, which is waiting in the SYN received state, receives this ACK, and on receiving this ACK will move to the established state. Now this is a typical sequence of state transitions that will take place on the client side and the server side. In addition to this, there are certain other transitions also which could take place. So that is what is depicted by these 2-3 other transitions that we have over here. Now when I am in the listen state, the server is in the listen state, it could get a send from the application saying that I want to send data to a particular machine. So in which case what you do is you will send out a SYN packet and move to the SYN send state and again wait for a SYN plus ACK to come. Okay, that is a possibility. On getting a SYN plus ACK, you send out an ACK and move to the established state. This is one possibility. Another possibility is that when I am in the SYN send state, that is I have sent out a SYN, at the same time the other side also sends a SYN. So that is I am in the SYN send state, I am actually waiting for a SYN plus ACK to come, but what I receive is actually a SYN. So if I receive only a SYN, then I send out a SYN plus ACK in response to that and move to the SYN received state. In this state, all I am waiting for now is an ACK to come. When an ACK comes, then I will move to the established state. Okay, so these are the different possibilities that we have for the for any TCP process to come from the closed state to the established state. Okay. Now, in any of these states, if a closed signal is given by the application, it will take it from the listen state or the SYN send state back to the closed state. Okay, this is how the connection establishment process is done. Once the connection is established, then you have flow control, congestion control and various things that are happening within this established state. Okay, we will take a look at those details later, but now let us look at how the connection closing takes place. So if you look at the state transition diagram for the closing part, now you are in the established state. Now there are two events that could happen, right? One is that the application tells you to close, in which case you go out and send a FIN. The other is that you have not yet closed the data transfer, but the other side is sending you a FIN. Now both these are depicted in the same transition diagram. So let us look at the various transitions that can happen in both these cases. So let us say the application sends a close. So what is the response to that? TCP will respond by sending a FIN to the other side and wait for a FIN to come from the other side. So it goes into a state called the FIN wait 1 state. Okay. Now let us look at what will happen on the other side. On the other side, it will receive this FIN. So on receiving a FIN, your response to the FIN will be you will send an ACK and you now go to a close wait state, meaning that you are waiting for the application on your side to close the connection. When the application says close the connection, then you can respond by sending a FIN. Okay. So right now you have sent an ACK for the FIN that has been received from the other side. Okay. So on receiving this ACK, look at what happens now back to the other side. On this side, I have sent a FIN, I am waiting for a FIN and an ACK to come from there. Let us say I first received an ACK. If I receive an ACK, then I go to another state called the FIN wait 2 state, where I am waiting for a FIN to come from the other side. Okay. So this is the state I will be waiting in. Okay. Now let us look at what happens on this close wait state. In the close wait state, if I receive a close from the application, then I will respond by sending a FIN. On sending a FIN, this the other side which is waiting in the FIN wait 2 state receives this FIN, sends out an ACK and then goes into something called a timed wait state, where it waits for about 2 maximum segment lifetimes before it will go move to the closed state. Now I will quickly tell you why this time wait is required, but before that there are other possibilities that we have. Now I told you that when by the time I receive a FIN, if I also have received a close, then I would be sending a FIN plus ACK. So if I receive a FIN plus ACK when I am in the FIN wait 1 state, then I have received my FIN as well as the ACK. So I just respond by sending an ACK and then moving into the timeout state. Okay, that is possible. Or if I am in the FIN wait 1 state and receive a FIN, then I send an ACK and wait for the ACK to come for my FIN and then move into the time wait state. Now the time wait state to close state, we have this 2 MSL timeout, essentially to take care of some ACKs which could have been lost, which may have to be retransmitted. So we just wait for some time before we actually close the connection. On the other side, on receiving the last ACK, you come and close the connection. So this transition diagram captures the complete set of transfers that take place, both the 3-way handshake that is used for connection establishment and the 4-way handshake that is used for connection termination. So to summarize, what we have looked at today are the following. We looked at some of the details of the TCP protocol. We looked at the header format. We saw that muxing and demultiplexing are handled by means of port numbers. We looked at the connection setup using 3-way handshake. We looked at the flags. We looked at the connection tear down process and the state transition diagram that is used for this purpose. Questions for you to review the matter that has been done today. Question number 1, what is the primary function of the transport layer? Question number 2, what are the techniques used by TCP to provide reliable data transfer? Question number 3, what is the size of the standard TCP header? Question number 4, what is the purpose of the sequence number field? Question number 5, How does a three-way handshake for connection establishment work? 6. What are the flags used for closing the connection? Question number 7. What are the two types of open supported in TCP? Question number 8. Trace the events involved in a typical client-server communication. Thank you.